Okay, so welcome back. Now we're going to talk about comparing pumps through these things called similarity laws of pumps. But I'm taking this lecture to really highlight the process and the point of these laws. I think that's more important is how you get to these similarity laws for pump, because they express a lot of techniques when it comes to how to approximate relationships in engineering math. Okay, that'd be a bit better. Okay, some lighting issues. So first, let's just the idea of taking two pumps and maybe comparing performances of both of them. So they could be two different models. They could have different sizes, right? So this is pump one, pump two, right? So two different pumps, right? And they have these, they could have two different diameters associated to them, right? Remember in the first lecture of this stuff, we had, right, a diameter, and we had angular velocities. So those are really angular speeds that we designed the pumps for. So they can have different types of speeds we run them at. They could have different fluids that run in them as well. So we have like a density, viscosity as well. So they could have different fluids maybe that we're testing them at as well. And they could have all different kinds of other dimensions, let's say. So it's like an Li, tons of other dimensions. And just how do you compare? That's what we're going to get at. And eventually, even with the same methods, we get to this fantastic specific speed axis that will lay out types of pumps based on the same principles. So that's really cool. But just from starting out, you can just draw the image of two different pumps, and you could list out all of the types of variables that are involved with it. So this is a good exercise to do, and I think extra credit, I said do it. So for extra credit, I say do this for right. So do this process right here, but for like a hydroelectric dam or anything of your choice that involves fluids in motion. But just take the time to list out literally all of the variables of dimension that you just suppose have an effect on what you're looking at. Right. So for the pumps, I have my list right here. So for the pumps, right, draw it. Right. For centrifugal pumps, we have this image here, right? We have an angular speed, some diameter of the pump itself. What else do we have? Even flow rates. So they'll kind of get to like just list them out. So there's Li, which are just other lengths involved in the pump design. So it could be like an exit, right? This could be like an L1. Maybe the inlet's even different. That could be an L2. Right? Even like if there's something right here, say the impeller has actually like a width to it, right? That could be like an L2 or 3. So they go on and on and on, subscripted by I. Any sort of length that you could measure with a micrometer or measure with some little thing in your pocket, right? It would be here. So I sort of define, right? I think in the notes, and you'll see later why, these are sort of any not the diameter, right? And then clearly we have an impeller diameter, and that's a very critical one. That's, boom, like the size of the pump, right? Easiest dimension you probably can get from this. What else do we have? Well, recall that like you could, for any material, right, there's a roughness height. I always like to think about how you get that height. I think I went over that, but always remind yourself that like you can get this fairly easily with a little machine. So if you want to measure it, you can. It's not that hard. Using some tools for it. What else do we have? Well, clearly a parameter is flow rate. Right, and that's sort of what the pump, right, your system, right, whatever you're requiring, there's a flow rate associated with that. This is volumetric. Okay, else we have, right, and this is a big one. Angular velocity of the pump spinning, so how fast you're rotating the impeller. Clearly that has some, right, it has some effect on any sort of thing you're trying to predict. And then we also have fluid properties. So these are sort of fluid properties for incompressible flow. That's going to be constant. Newtonian flow, this is a constant value as well. Other sort of things you could do. If they weren't, you could take an average even. But these are definitely a great, a good list of sort of everything going on in the pump picture I have. And all we've done is very, very intuitive sort of descriptions of what variables would end up having to matter if you look to predict anything. Okay. So now let's shift into what do you want to predict? What are you trying to characterize with your pumps? What are you trying to get at? So, right, motivationally, right, let's just go back to these system curves that we have, right? What was this axis? If you're trying to figure out what you want to predict based on non-dimensionalization, which is where all this is headed, go to graphs that you look at and see what's my y-axis. So, right, it's right, the head of the pump is what you want a performance, or a delta P of the pump. So head rise for pumps is something you want to characterize. Recall on this side, the other thing is you had a separate y-axis you compared to, and that was the efficiency of the pump. So these are things I definitely want to predict, right, and compare about. Different pumps are categorized based on these y-axes, right? Every pump has its own characteristic curve, right? So one would look like this, another could maybe look like this, some, maybe one could even look like that, etc. Same with these. Each one of these pumps has their own efficiency plot that kind of, maybe look like this, something like this, maybe, they all have all these things. So combine these, you want to conjunct all these graphs into sort of a singular non-dimensional quantity. So that's sort of the idea is every pump has a different characteristic curve and a different characteristic efficiency, but by changing the quantities like diameter and angular velocity, can we predict what the new thing would look like without making it, or without actually producing that, without doing that experiment? Can we just do it non-dimensionally? And it turns out it works out, right? So, right, things we're trying to predict, it's just that, right? Right, pump head rise is something that we want to predict, right? And then it's kind of because we wanted to this, remember, this is defined as power taken by the fluid to the work shaft, what you paid for, what you get. So again, you're trying to categorize that. Things I want to power to the fluid, and then sort of shaft power, right? This is the money, the cost that goes into running this. This is what this is the power transfer to the fluid, and that's what you get. Okay, so those are the three things you want, and that's what we're going to look at into non-dimensionalization. So these are really the dependent variables that we care about when it comes to a pump. It's really how we evaluated any pump that we got, was this idea of draw some plots on these axes and then look at the flow rates. But it was sort of a combination of three things we always looked at. Those were the dependents, right? So, right, we had head rise. Dependent, right? These are the things that are going to depend on how I design the pump and its lengths and its dimensions, right? And then that other list were all the independent variables, right? Or the assumed independent variables is really what you should say, right? So where is that list? I think I had it right here. Just want to, okay, yeah. So then you have these ones. And again, this is actually I, so this could be like N. I could write a bunch of these out. It's any sort of dimension I decided to put on. Epsilon. Okay, and these are the independent variables of the pump. Okay, of the pump. I have control over these. I don't. It just ends up this way. Right, so now we're gonna. So that's what we're getting at. So the idea is these all depend on somehow these parameters of what I design. So, right, the statement we're mathematically making is an existence statement. Right, we're saying there exists three functions that you don't know what they are. Let's call it F1. Okay, three functions exist. Okay, this just means they bring the same arguments. That's what we've done with all that analysis, and it took a little bit of work. It didn't even seem like analysis, but I promise you sometimes this can get hard. You're listing out a bunch of independent things you just assume are what caused the changes, and then you have to think about really what are the things you want, what are the dependent things that you care about. So it'd even be hard for me to even tell you like why you would have cared about finding the head, the power, and then this. These two give you that efficiency plot. So the one before, I showed you all the reasons you select a pump, and now with this process of non-dimensionalization, getting similarity laws to really like compare pumps, it'd be hard to motivate why you would want these three variables. And even still, the first lecture helped identify in turbo machinery, right? That was all. I'm just drawing a bunch of pictures really to show you why you would arrive at these independent variables that clearly would have some effect on whatever you're trying to predict. Actual headrise. Okay. So these are dimensional functions, right? So this has dimensions, this has dimensions, and this has dimensions. These similarity laws, what they break down to is to non-dimensionalize these functions themselves. Non-dimensional functions are great because they're true for a much larger set of a much larger set of designs, right? They're not restricted to even units, which helps. I love non-dimensional things, so. So we're going to just naturally go through this process of how would you do this non-dimensionalization process. I have a pretty rude statement in there about Buckingham Pi in my notes. Those are just my thoughts, but I like to do it this way. Because if you do all this process like non-dimensionalizing and listing this out, you just get a better sense of why you'd even want to do it and what you gain from it. Okay, so to non-dimensionalize, we need to create non-dimensional head rise, non-dimensional power of the fluid, and non-dimensional work of the shaft. So non-dimensionalizing meaning, well, how do these variables scale like? Forget about the independence for now. What we're after then, to non-dimensionalize these functions, you don't even know what they are, right? Arbitrary functions. You have no actual idea it's not exponential, it's not a tangent, you don't know what it is. You're just saying there exists some sort of function. It could even be discontinuous, right? It's just talking about there's some relationship. There's an input-output when it comes to pump parameters to these things. So for non-dimensionalization, you ask yourself, well, what does this scale like? What does this scale like? And what does this scale like based on information I can use? So what is the head rise of a pump scale like? What values would I expect to see of this? And that's good non-dimensionalization. So one thing is we want to refer to, right, the pump. We want this to, right, we want this side to refer to quantities involving the pump. Okay. So breaking this up, I will do that non-dimensionalization next.